Deflection of beams. Theory explained. Welcome to Blueprint to Reality, where we simplify complex engineering concepts. In this episode, we'll dive into deflection of beams, an essential topic in structural engineering that ensures the safety and performance of structures. What is beam deflection? In simple terms, deflection refers to the bending or displacement of a beam when subjected to loads. Imagine a ruler placed across two books. If you press down in the middle, it bends. That bending is deflection. In real-world structures, beams are designed to carry loads like people, furniture, or even heavy machinery. However, as these loads increase, the beam experiences deformation. This deflection, while small, must stay within safe limits to avoid structural failures or discomfort for the occupants. Why does deflection matter? Excessive deflection can have serious consequences. 1. Structural damage. Over-deflected beams might crack ceilings, walls, or floors. 2. User comfort. Too much deflection in a floor beam could make it feel bouncy or unsafe. 3. Aesthetic issues. Sagging beams ruin the appearance of structures. By understanding and controlling deflection, engineers ensure structures are both safe and visually appealing. What influences deflection? Let's break down the factors that influence deflection. 1. Beam material. Stiffer materials, like steel, deflect less than flexible materials, like wood. 2. Beam shape and size. A thicker or deeper beam deflects less than a slender one. 3. Load type. Point loads, like a heavy weight in one spot, cause more deflection than uniformly distributed loads. 4. Span length. Longer beams deflect more because they have less resistance to bending. Each of these factors is accounted for when designing beams to ensure they meet safety and serviceability requirements. How do we calculate deflection? To calculate deflection, engineers rely on formulas derived from beam theory. The most commonly used equation comes from Euler-Bernoulli beam theory, which considers moment of inertia, I, a measure of the beam's resistance to bending; Young's modulus, E, the material's stiffness; load, P or W, the force or pressure acting on the beam; beam length, L, the span between supports. Real-world applications. How is this theory applied in real life? For example, in a bridge, engineers must ensure the beams deflect within permissible limits under traffic loads. Similarly, in high-rise buildings, floor beams are designed to minimize sagging, maintaining comfort and aesthetics. By controlling deflection, engineers create structures that are both durable and comfortable, ensuring they perform well under real-world conditions. Conclusion. In summary, the deflection of beams is a fundamental concept that balances structural integrity and usability. By understanding materials, shapes, and loads, engineers can predict and control deflection, ensuring every beam supports its load safely. Thank you for tuning in to Blueprint to Reality. If you found this explanation helpful, don't forget to like, share, and subscribe for more civil engineering insights. See you in the next episode. Advancements in nonlinear structural analysis. Imagine pushing a spring. At first, it compresses linearly, responding predictably to your force. But then, something changes, it twists or buckles unpredictably. That moment when things no longer follow simple rules is the realm of nonlinear structural analysis. In modern engineering, this field unlocks the ability to predict the unpredictable, ensuring safer designs for complex structures. Today on Blueprint to Reality, we dive into advancements in nonlinear structural analysis, what it is, why it's essential, and how it's revolutionizing the way we build. What is nonlinear structural analysis? Nonlinear structural analysis is the study of how structures behave under conditions where the usual rules of proportionality break down. In linear analysis, force and deformation have a simple, predictable relationship. But real-world structures often face scenarios where this relationship becomes more complex. Examples include large deformations. When a structure bends or stretches significantly, its behavior changes, requiring nonlinear models. Material nonlinearity. Materials like steel or concrete behave differently when stressed beyond their elastic limits, transitioning to plastic deformation. Boundary and contact issues. Components in a structure may shift, slide, or lose contact entirely, affecting stability. This field answers questions like, what happens when a bridge cable stretches beyond its limit? How does a skyscraper respond to seismic shocks that push it past its designed elasticity? The need for nonlinear analysis in modern engineering. As structures grow taller, longer, and more complex, linear models fall short. Skyscrapers designed to sway in the wind, or suspension bridges that endure earthquakes, require more nuanced predictions. Nonlinear analysis allows engineers to anticipate failure modes, predict how and when a structure will fail under extreme conditions, optimize materials, use advanced materials more effectively by understanding their nonlinear behavior, improve safety, create designs that resist unforeseen forces without catastrophic failure. From space exploration to high-speed railways, nonlinear analysis is at the core of engineering innovations. Key advancements in nonlinear analysis. Computational power. Advanced algorithms and powerful computers now allow engineers to simulate nonlinear behavior with unprecedented accuracy and speed. Finite element analysis. FEA. Tools like FEA can model even the most complex scenarios, breaking structures into smaller parts for detailed simulations. Machine learning. AI-driven algorithms analyze vast datasets, predicting nonlinear behavior faster and more reliably than ever before. Multiphysics simulations. Engineers can now combine nonlinear structural analysis with other fields like fluid dynamics or thermal effects for holistic designs. These advancements are transforming industries, from building earthquake-resistant skyscrapers to designing flexible aircraft wings. Real-life applications of nonlinear analysis. Nonlinear analysis isn't just theoretical, it's saving lives and pushing the boundaries of what's possible. For example, skyscrapers. Engineers use nonlinear models to ensure that buildings remain stable during high winds or seismic events. Bridges. Nonlinear analysis helped design the Millau Viaduct in France, allowing it to withstand extreme wind and thermal expansions. Aerospace. Aircraft components are tested under nonlinear conditions to ensure performance under varying pressures and temperatures. Why these advancements matter? The stakes couldn't be higher. Nonlinear analysis doesn't just prevent structural failures, it enables engineers to dream bigger, building safer, more resilient structures in the face of natural disasters, climate change, and increasing urban demands. It also means more efficient use of materials, reducing environmental impact while saving costs. Conclusion. Advancements in nonlinear structural analysis are reshaping the world around us. By understanding complex behaviors, engineers can predict failure, optimize designs, and ensure safety like never before. Thanks for joining us on Blueprint to Reality. If you enjoyed this exploration, don't forget to like, subscribe, and hit the bell for more insights into the cutting edge of engineering. Until next time, keep building smarter, safer, and stronger.